Good afternoon, everyone. Thanks for your attention. My name is Patrick Feng from BYD Microelectronics. For those of you who doesn't know BYD Electronics, it is a wholly owned subsidiary of BYD Company Limited, Shenzhen, China. The corporate level company, BYD, have three product groups. One is we make cars, so BYD is BYD brand. The second product area is our IT group. So we make cell phones, OEM and ODM for other brand name cell phone companies. And associated with that, we also provide components, modules to support the final product. The third product group is the, we call it new energy. So it involves solar energy storage using lithium iron phosphide battery technologies. Three product groups. So back to BME, we were formed in 2004 and focusing in the semiconductor ICs and applications. So the product areas involve four areas mostly. CMOS image sensors, touch solutions, power management ICs, and power devices. So I'd like to take this opportunity to bring everybody some senses in terms of the CMOS sensor markets, also the CMOS sensor applications in different areas, especially in the cell phones and also in automotive, and also some of the industry efforts or directions to meet those applicational requirements, and how to resolve some of these questions. This is the general market trend of CMOS sensor revenue. If we look at it this year, and last year is over $6 billion, and this year is about $7.5 billion, and going at a compounded ratio of 11%. As you can see, the CMOS image sensor applies in a wide range of applications, from the highest volume mobile handsets to consumer level, like digital cameras, and computing, automotive, medical, surveillance, security, and industrial applications for recognition and alignment in these areas. Very wide range of applications. And also, and if you convert this over to capacity, it's a huge quantity of wafer needed per month. 500 wafers. Apologize for a typo there. So also, but if you look at the growth rate in the new and emerging applications, like in automotive and in some smart TV and home appliances, the growth rate actually is much bigger. This comes to the very well-known chart of categorized applications. And if you look at the lower right corner, it's the most high volume, very demanding. Look at the cell phone shipments, it's over 2 billion. And with smartphones, much bigger, most of them at, with one or two image sensors. You can see the units for demand in CMOS image sensor can be over billions of units. But if you move upwards to the upper left corner, and we come across the security and come across those automotive, and come to very specialized medical systems and machine vision. Those areas, the volume goes down, but the performance is much more demanding. So there's a balance act between the market sizes and also portability. Like, for example, in mobile situation, portability is very critical. Since we have to pack things into small areas and thinner phones. But in those areas, space may not be as critical, but in terms of noises, for example, in X-ray situation, the noise level has to be low enough to provide a very high dynamic image, up to 16 bits. The consumer level 8 bits probably is good enough. But going to the higher, going to those higher end applications, it goes up to 16, up to 20 bits. Over 20 bits type of resolution are needed. There are 3 areas I think are most active, in my view, in demand growth and innovation. Mobile obviously is one, as everybody can see it. Another area is the security, because of the CMOS image sensors are shipping into the traditional CCD surveillance and security area. So that's one area really exciting. Automotive, because the machine-assisted applications will improve safety and convenience significantly. So this is one area demands a lot of innovation to meet those new application needs. It involves chip architecture and circuitry design, packaging, and also, most importantly, wafer process to guarantee the performance as well as for the cost performance. Back to the cell phone situation, if you look at this, and we came from almost like a quarter of a VGA resolution all the way up to 241 million pixels with Nokia's 808 cell phone. It has gone up significantly. So for higher resolution, for differentiation in full cell phones is straightforward. But on the other hand, if you look at this, some people argue, say 4 million pixels is good enough. Like most recent top line cell phone from HTC is called HTC One, is using 4 million pixels. If you print the image out with the 8 inches paper, it's sufficient. You won't be able to see the pixels. It's a smooth picture. But some other people argue, well, if I use this one, I can do digital zooming effectively without involving a very bulky and complex optical zooming system. So going up may be a pretty important thing to do. But of course, going up makes the chips very big and also the modules very tall. How to pack things together would be another factor for our designers to consider. Of course, by moving, if you look at this, this is one example. As of today, this phone comes from China with less than 6 millimeter thick. It's a 5-inch display with an 8 megapixel camera and a 5 megapixel on the front. So compared with iPhone 5, which is over 7 millimeters, so this one does have a pretty aggressive push towards a thinner, more lightweight result in that. And correspondingly, the module is lower than this rate because you have to take into account the cover, you have to take into account some of the PCB inside. By breaking down into the camera module, you see lens, you see holder, and you see the PCB underneath it for connectivity and the socket. And all these things add together. That means in order to keep a good field of view for our imager, we have to, in order for the height to shrink, this imager has to go shorter also. And from that standpoint, you see the industry is aggressively pushing to go from the old days of 3.6 microns all the way down to 1.12 now. So the popular version for the high resolution imagers are 1.4 to 1.1 these days. So that effectively helped to shrink the scale of the image sensor and make the modules shorter.
Okay, but if you shrink the picture smaller, if you see the so-called fill factor, that means even though you have 1.4 by 1.4, but only a portion of those 1.4 areas are sensitive to light. There are other areas allocated for the circuitry. So there's a so-called fill factor involved. So when you scale down the pixel size, the field factor goes smaller. So all these factors add together, the sensitivity become a crucial factor because the deterioration of the light coming into each pixel. So there are different approaches to address those. For example, we are taking like light guide. Dongwu is a big player and working in this area. And BSI called backside illumination, which will help to increase the sensitivity without, compromising on the pixel size. And also there are color filter areas which can improve those performance as well. For cell phones, obviously, cost is very sensitive. So one of the approaches by retaining a good performance, reducing the pixel size, we are able to get more and more dye on each wafer. In this particular case, going to about 2,500 to over 500,000, 5,000 helps the cost down effectively, so that it translates to the competitive amounts at the cell phone level. Okay, we talked about the CMOS image sensor generally in the cell phone area, but in the automotive condition, things are very different because I use the term called demanding because a lot of the situations are very necessary. In cell phones, if you see a dark area, you cannot take a good picture, then we live with it. But in automotive area, a lot of times you have to somehow resolve that difficulty and allow the drivers to take advantage of your vision systems. So that's why the very top of the line in this natural requirements would demand a low light performance, and especially a pure darkness night situation. So that means we have to have a good low light sensitivity. Come to think about that, a lot of the image sensors in the automotive area are still at a 5 micron by 5 micron pixel, and the sensitivity compared with the cell phone, the cell phone situation is 10 to 20, let's say, x more sensitive, so that you can retain a very good smooth frame rate of 30 to 120 frames a second, and in the meantime, create a very light view of a very dark situation. And in case it's complete darkness, so there are approaches like using so-called active systems. So basically, we shine a visible beam, an infrared beam, for example, to brighten up the front view for the CMOS sensor to pick up the image to clear things up. The so-called passive is probably beyond this topic. Usually, it's a solution where we involve 10 to 14 microns of infrared using for the thermal imaging to do all that. In the rainfall snow areas, it's very difficult as well. So as most people have experienced, this is when you have very low visibility. You have to slow things down. So how to address that? As far as my company is concerned, we have been looking into, but this is generally one area, like using gated image by putting pulsed illumination, very short pulsed illumination, to gauge the reflection of a certain distance to form images at that distance. By doing it this way, we ignore all the reflections from other distances to interfere with your image, so we can clear things up. So clear things up in this kind of a foggy or rainy situation. High speed is straightforward to everybody. Of course, the cars are moving fast, so we need to do that. High contrast, like in this type of situation, we like to see anything beyond this bright spot, what's going on there. That demands a high contrast situation, like high beams or sun when we are driving into the sun. Higher temperature is straightforward as well. That means we have to address the sensors' dark noise and hot pixels to minimize those noises at high temperature. Higher resolution with intelligent applications in automotive. The cars need to recognize those road signs, like the stop signs, or the highway numbers and things like that. And so reasonably high resolution is important. Unfortunately, currently most of the still at a D1 resolution, so basically 300,000 pixels count right now. But I think going to higher resolution is the destined direction to go. The last one I think is very important is called distance sensing. To do the collision warning or collision avoidance system. So instead of how people to recognize that, we can use automated systems to do that. But there are many ways to do that, like using, generally speaking, time-of-flight approach, or we could use the so-called modulated phase delay approach, or using the stereo vision, for example, having two cameras in the front, looking like two eyes. We can do the algorithm correlation to find out the images, the objects in the image, how far away from it. You know, one of the car companies like Subaru is already commercializing in one of their cars, legacy cars using stereo vision. And that's directly related to CMOS imaging. We could have two CMOS images and standard CMOS imaging sensors to do just that. Okay, back to this simple application now. This is called a rear view system. And this is called the panoramic view system, where you have 4 cameras. This is our BYD van with 4 cameras, one in the front, one in the back, and 2 on the side. And combining the image, when you are backing up into a parking spot, you can literally visualize your car like you are looking down from the top. So it's much easier to park it than doing it this way. Another quick point, the U.S. National Highway Traffic Safety Administration has proposed a mandate. It didn't get the approval because automakers say it's too expensive, but I think the cost will come down quickly, so that I think this will become a pretty natural must-have in each car for the rear view system. Night vision. In this particular model, BYD has, what we have is we have IR-assisted navigation system with a typical CMOS image sensor. So basically, we shine the light over to the scene so that we can have a highlight there. I mean, a lot of times during the night, the dark close people are the most difficult to identify. But with the infrared, actually, you see them in the other contrast. It's much easier to find out. It has 100 meter of over 100 meter of sensing distance and works pretty well. They use conventional small sensor, has a high dynamic range, and it could be power modulated to improve the oncoming traffic approaching. Another area in that is to improve the high dynamic range. This is a conventional small sensor. If you're in a high contrast situation, expose the interior, you overexpose the outside. But if you expose for the outdoor and indoor, then you expose. So our image sensor have one approach to take so-called intra-line approach to intra-frame approach to combine 2 images together, so that when you are driving through a tunnel, before you get out, you can see outside tunnel as well as see, relatively easier to see what's inside. So that would be a great benefit for the drivers. Everybody knows Google has driverless, and some people call it self-driving cars, and it has this LiDAR system for distance and for the environments. And there are other things, but 3 critical areas. One is object recognition, obviously for sign recognition, range sensing, basically for distances, and it has to identify lanes and also identify those road signs and people. So, and also have to work day and night conditions. For high frame rate, obviously for moving objects, we need a higher frame rate, 60 hertz, that's frame per second, up to 120 frames per second to freeze up things. But there's one issue with this image sensor, even with higher frame rate. It's called a global shutter issue. We'll talk about that later. And also higher resolution for recognizing, better resolution for recognition. Okay, here we go. The rolling shutter, most of the imagers are using rolling shutters. It's very effective. So what does that do is it scans, it resets and read out the integrating time for one line at a time. So different line of the imager have a different exposure location. So when you are moving, like this picture was taken like by the iPhone, actually. All the phones now, by taking this, will do the same thing. So in a moving car, so those lamp posts or those suspension bridge lines are supposed to be vertical, but because of the moving, the wrong shutter effect, it deforms it. So I have to address that by so-called global shutter approach. But we have a penalty on that because the pixel needs more transistors, and which needs bigger, costs more. And this is probably the toughest one facing in the automotive application, is in the rainfall snow situation, how to do that. That's the one. Another one is especially in China, and when a lot of people use high beams very often. And like in the US, when you see oncoming cars, you turn the high beam automatically. But in some other areas, people do that. So making things quite difficult. So some of the solutions like assisted beam, so we can send a pulsed beam over to illuminate the upfront objects. In the meantime, by using global shutter to shortening the exposure time, to minimize the exposure of this continuously incoming light, we are able to reverse the contrast. So have a pretty strong reflected image, but a very minimal incoming image to minimize these effects. Okay, back to the CMOS image sensor. This is a very typical architecture of an imager. You have an imager array. We have some decoders to address this array to scan things over or reset and read out. And also we have an area we call analog processing to get rid of the noises and also unevenness of the imaging, and going to the ADC and so on. But most of the critical areas in this imaging array, so we have to look at the sensitivity, we have to look at the dark current, the leakage, and also look at the hot pixels where it pumps out bright spots, even though there's no light coming into it. So those are the areas we need to address with this pixel. How to address that demands quite a bit of design collaboration between the process and also the design engineers. Okay, sensitivity is the key, I think, for image sensing. So this is one area we've been working with Longboard to address those. This is the standard called a front-side illumination approach. Longboard has done very advanced approach by lowering the pixel area highness so that the image sensor already have a reasonably excellent sensitivity. By lowering, if this color filter is at this level with multiple metals, like 3 layer metals or even more, then you will have a very shallow, very small tunnel having light coming in, making this image sensor very less sensitive. So they have been done a great job to do that in the sensing area, to especially make the top layers smaller. But even further, by putting a light guide inside, we are going to be able to improve the sensitivity significantly. Depending on the edges and also the center, there will be a wide, and also the uniformity. If you look at this image, the center is brighter and the corners are darker because this straight tunnel is, and when the ray is coming in sided, it doesn't go in as much as the ray coming straight down. And also for the second generation, we're going to combine a light guide with deep photodiodes to improve the sensitivity as well as improve the so-called full well capacity. This is another term very critical to image sensor pixel. It is by doing that we are able to have the pixels handle higher dynamic range situations. When the bright spots, the light coming in, they don't saturate as much as otherwise. So these are the great process improvements we've been working with our process vendor. Another large area, you heard it a lot, is called BSI, it's called backside illumination. What it does do is, in this so-called front light situation where a light has to go through the micro lens and the color filter, and going through a lot of layer of metal, very long trip to the sensing area. During this time, they got blocked and scattered by those structures. So create a darker image, less sensitive image, and also non-uniform for the corners especially. But what the BSI does is they thin the wafer down and put another on this side. I'm sorry, and put another substrate layers on the top, so that the light will come from behind like this, so that it's straightforward coming in. That significantly improves the efficiency of light collecting by more than, I say, 80%, or depends on the front side comparison, but will be a significant improvement in those areas. And there are other areas, further type of PSI involves, this is the typical PSI. Then later on, we can effectively get this circuitry out into the other side of another wafer. So making this fill factor close to 100%. So that further improves the BSI effectiveness. Another direction to go is this is the so-called traditional layer pattern, RGB blue, the pattern. But one new area in the industry is putting a white pixel in this process. So it's called RGB white. And what this do is, one of the images will take those ones, and they will be effectively about 3x brighter than this filtered version on the average. So by combining the image of this black and white versus the gray image versus those colored ones, they are going to form much effective sensitivity improvement. This slide is trying to show that there are different architectures where we can try to address some of the special applications. This is the old day, very passive pixels approach. Most of the devices are using this pixel array approach with like a 3 transistor active pixel, 4 transistor active pixel for rolling shutters, and going to 5 pixels, 6 pixels, 7 pixels for doing global shutters and other applications. And for the column processing, could it be a pure analog approach? It could be, called a column-based ADC to convert every column signals into digital forms at the column level. And this pixel parallel news rate requires decision making at the pixel level. So it is especially for other applications, especially in the automotive or other high-speed applications. Okay, here again, regarding to the global shutter, how to address that. This is a typical rolling shutter for 4-pixel approach. We do have this side effect when the shutter is coming down and the fan is, this default fan is coming down as well, so you see the unnatural expansion. But by putting a global reset transistor over here, we are able to realize this global shutter timing so that all these pixels are reset at the same time. And also, we start holding this pixel signal at the same time and read out them sequentially. Regarding the high dynamic range, there are many ways of doing that. One way is using larger, small pixel combination. Another one is using a so-called intro frame approach by
reset, effectively read out 2 frames at the same time, one with a longer exposure, one is with a shorter exposure. And we are combining, naturally combining those 2 into a high dynamic range image. It has capacities that it can support video. And for the multi-frame HDR, it has better performance, but only do it usually in a still camera situation. Okay. So here in summary, I like to say the CMOS danger for cell phone and automotive or surveillance present very exciting and a different type of challenges. And collective efforts in wafer processing, image design, and system applications are providing end users with better solutions. And we are still have areas for technical solutions from everybody. Thank you very much.